Everyone, and welcome back to the Information Bottleneck. And today we have Cody from Datology AI, who is doing really interesting work about data curation, one of the most important and underappreciated aspects of training LLMs. Cody was previously at Mosaic, and he has been thinking deeply about actually what makes training data good. So welcome to the show.
Yeah, thank you for having me.
And Ellen, good to have you here as always. How is doing?
It's good to be here, and it's good to meet one of the people who's really pushed AMD GPUs hard, right? Because that's kind of what Mosaic was known for at the time. So we'll definitely want to go into the dynamics around that later in the call.
Man, I had forgotten about that, yeah.
So, Cody, let's start from the beginning. How did you get into data curation? Like, was there a moment you realized this was a thing to focus on?
Yeah, so that's a great question, and, I do sometimes look around and wonder how did I get here? Uh, my, like, entire career at this point has been thinking that I was going to do one thing, and then looking around for something that was, like, very high leverage and then ending up doing something else. So like, when I did my PhD, I didn't really know what I was going to do it in. I was very close to being like an HPC, like kernels person, like writing high performance parallel GPU code. And when I started working on my PhD, I had talked to my advisor. I was really excited about this AI thing and how can we like bring it to devices. Right at kind of like a critical point where I, may have gone in the other direction, I read Jonathan Frankel's lottery ticket hypothesis paper. And I was like, oh, you know what's way better than faster kernels? Like faster models. And I kind of like went on this whole journey doing like pruning and distillation, and I think the first time I had realized that data was better, there was this paper where I was hoping to write on distillation, and I had this problem in my training. And I like there was this weird data set. I was just kind of trying a toy example, and it was like something on the TensorFlow data sets at the time, just some weird like pictures of like crops in like Africa or something to help like farmers. And I found a handful of examples in it that like completely destroyed my training, and I pulled them out, and then the distillation worked really well. And I was like, I think I have the world's best model on this data set. But like in my like, young researcher brain, I couldn't figure out how to make this a paper about distillation. So I just like threw it away and like went about my life. Yeah. And so then I had spent some time in my PhD at Meta. Ironically, I think I was actually on a team that was basically what Mosaic ML was for everyone else inside of Meta. We were like a consultancy for like infrastructure, and we were the modeling team. So the rest of the team did like set up physical servers, and like there was a day where like the power, like everyone's login went out, and like they had done like the face logins for the building were through that service, and someone in my department had to break into like Meta headquarters with an axe to go physically reset the servers. But like I was on the modeling team. It was just kind of weird how that worked. But we did consultancy, so like the ads and content people would come to us and they're like, "Hey, our model's slow or our inference is slow. How do we make the modeling better to make it go faster?" And it turned out to be like a pretty useful skill set when I went to Mosaic, and that was how we did everything. It was like, okay, training is, how do we make training go faster? And I had never really expected to work on data. Even when I was doing all this stuff, it was a bunch of algorithmic improvements, distillation, things like that. But then when we started training the MPT models, like we just needed tokens, and there was like, okay, well this is the highest leverage thing I can do. Is like we don't know what good data is. We have a lot of data, but most of it looks really bad. And how do we make this into a good model? And so like once again, I like left my comfort space and did something that, data work kind of sucks. Like it's not a lot of fun. And a lot of people don't want to do it. They don't want to think about it. But it turned out again, it's like very high leverage and makes really good models. So I went all the way from I'm going to write CUDA kernels too. I have to stare at weird, like, pieces of text from the internet, and that's my job.
So from your perspective, like if you need to rate it, how much is the data versus how much is the model in general?
Yeah, this is a good question. And we had these debates a lot while we were working on DBRX, because we were hoping to be the first open source MOE, and we missed out by like a couple months to Mistral. But we were really excited about the performance gains you could get from MOEs, and I think we had like clocked them at maybe like 4 to 8x improvement. I think by the time we got done with this, we were seeing equivalent improvements from data, so like another 4 to 8x. I think now you can probably get like even higher than that, right? So like you need scale, you need flops, and you need modeling improvements. But I think, anywhere from like half to 75% of models performance can come from data if you do a really good job.
So real quick, around that time when Mistral released, I'm guessing you're referring to Mixtral, right? Was the
Exactly, yeah.
So I noticed that the field seesawed and arguably continues to seesaw between dense and MOE and sparse MOE models. I have a hypothesis around that related to log probs, because log probs look a lot different and spikier with MOE models. But independent of that, do you have any reasons that you believe that that's seesawing has happened and arguably continues to?
Oh, yeah, absolutely. I mean, for one, they're just like really hard to train. Like, they've got all these, theoretical benefits, and they're not theoretical, like they're practical. But especially like 2 years ago, training an MOE like sucked. It was it was not a good time. Getting reasonable MFU was really hard. And then once you got the MFU, there was all sorts of weird stuff that could start happening in the middle of training. If you didn't know how to do scaling laws to predict what you should happen, right? Like, we had all these scaling laws that were defined for dense models. They just like don't work for MOEs. I mean, like
My
a
gosh.
lot of good work has come out then. And so this is like much easier, but like, we were calculating like tokens to parameter ratios, and we're like, is it the active parameters? Is it the total parameters? And is it something else, and it was just like really hard to kind of scale them up in a reasonable way. So like, you can just train an MOE in Torch Titan now. It's just easy. Like you just import some things and go, and you've got not the worst MFU, and that's like, yeah, you can just do it. Dense models just solved a lot of problems, right? If you had enough compute, and you were willing to train for a long time, you had all these great scaling laws, and you go, okay, I'm going to hit my model quality target, right? Yeah, I think a lot of the reasons are just practical.
Yeah, I was just gonna say, I wish we could clip you, and maybe we will, on saying, about how those scaling laws that for dense models don't apply, because often people on Wall Street think that there's like one concept of scaling laws, and I'm like, I have personally seen hundreds of different papers, including workshops, possibly in the thousands at this point, claiming to establish a scaling law for something very narrow,
Yeah,
right?
yeah, absolutely.
But we
Yeah,
talk a
so
lot about scanning loss. We talk a lot about scanning loss with Alex Alimi a few months ago, and like the bottom line was that like it doesn't really good in practice, right? Like if you have so many scanning laws, so why I care about them, right? They depend on so many parameters, so many factors. So yeah, if you scale the data or like you scale the compute, you will get better results. But besides that, what can I get from it?
yeah, I mean, I guess like in isolation, the scaling laws are not that useful to know. But I think what is useful is when people can demonstrate that something is like measurable and predictable. This is like a great tool for you now, right? Like, if you are going to train a model that you want to release, you want to know which parts of your training are predictable, right? I mean, not the least of which are just like which learning rate to use, and how long can I train before, like, am I going to hit my target quality? The target quality is always just like whatever's the best model in this size this year, you know, and being able to predict out like, will the model that I'm going to spend, sorry, my dog has something to say about scaling laws too. you know, she gets very excited about this. You
All
know,
of us, it's okay.
yeah. You know, whatever, am I going to spend $10 million, $20 million, $100 million? Is the model going to get where I want it to be? Am I going to be successful, or am I going to fail? Right. I think that's really the only scaling law that matters, is like good model or not. Right. Yeah.
Okay, so we have the data, we understand that the data is important, right? Now, what you are going to do, how we are actually going to make better data for our models, what we need to care about, like how we are going to do it, what are the parameters they are going to measure.
Yeah, I mean, this is a great question. And maybe I don't know if y'all mind, but maybe I can answer this question with like a bit of a history lesson about, you know, what I learned doing this wrong.
Great.
And yeah, I mean, so like pre-training data is very different than post-training data, because it's a lot less intuitive, right, about what you're going to do. Like you can look at a lot of the data, and it's not as obvious what is helpful to the model. You know, like
Let's let's start with what does it actually mean pre-training versus post-training, right? For like
sure,
for
sure.
the 5% of the people that don't know these terms.
Sure, right. You know, all of your pre-training, I mean, well, this is a bit of a philosophical question, but generally, right, pre-training is the generic, very large autoregressive next token prediction, where you're going to be training on, you know, trillions of tokens generally. Post-training might include, you know, an SFT stage where you're trying to teach it some amount of instruction following. It may just be autoregressive. It may have some sort of like mask to like prevent training on the instructions. Depends on, you know, whatever flavor of this you prefer. And then generally some sort of RL for preference tuning, or teaching it reasoning, or like verifiable tasks. So the, you know, those sort of things, you typically see, you know, some, you know, pretty sharp like distribution shift and scale, and even like learning objective changes in the post training, whereas pre training is just like huge volume autoregressive next token prediction. And I think we'll get to it in a bit, but like this whole thing of like mid training has emerged, and you know, it's confusing because it's still pre training most of the time. So what makes it mid training? You know, and I guess it's because it's not pre or post; it's in the middle. And so yeah.
I
Okay,
just
so
want to. Oh,
yeah, then
sorry. I just want to quickly ask. When you're saying like, well, two questions. Are people, I know at one point people have, and in general, it seems like as we've gone deeper into scaling, the number of epochs trained, at one point it was 100 epochs that you would train something on average. Now I've heard it's well less than one on pretty much every, like, you know, GPT-5 or type model. And then two, is mid training when you intervene somewhere like deep in that almost one epoch?
Yeah. I mean, this is a good question. So, yeah, like you know, there was a bunch of literature that came out maybe like 2 or 3 years ago, which is in the ancient times now, uh, about kind of how many epochs you can really do on text data, right? Because you're right, like in the vision world, we did hundreds of epochs, thousands. I mean, if you add distillation, you could do millions. um and but this did like just didn't really work in text. And I think mostly the reason why it didn't really work was because there just weren't good data augmentation techniques, right? You can't train 100 epochs if you don't do random crop, flip, you know, noise, whatever, right? And that just like doesn't exist in the same way for text, or at least not like in a compute cheap way. But yeah, so like, you know, the you know, there are limits to how many times you can repeat data, and like for some of your data you won't go through it at all, or you hope you won't, right? And then there's some data sets, when, you know, sub data sets when you're doing your mixing, that you'd really like to see almost all the time, but you're kind of limited by these heuristics, right? And you kind of go, okay, actually, I'm going to try not to use this data more than 4 to 8 times. And then the question, the question, like the fundamental question of mid-training actually is, how do you use this data the best over the course of training? If you have 4 repeats, 4 epochs of this data, where should it go? And why, right? And that's kind of the whole game.
Okay.
Okay, so
Oh, sorry. No, you go, Ravi.
no. So I want to know, like, okay, so now I have all the data. We did like now we split it to pre-train, mid-train, and post-train, right? Like the different types of data. We can discuss how we are going to do it, like maybe later a bit. But let's assume that we have it. Um, then what?
Well, you write a big check to Jensen and you cry, and then you train the model, you know?
No, but okay, but like, okay, what is the like? Do we feed all the data to it? What we are going to do with this data?
Sure. Do you mean like practically? Like, how do you get this to work?
You, you can start with high level. Like, what do you want from this with this data? What do you want it to really represent? What types of data you want? What are
Sure.
the like? What is the relationship between the tasks and the data?
Sure. Yeah, okay, I see where you're coming from. So, fundamentally, we want models that are good at things, right? And if you're releasing open source models, or like frontier level models, the hard part is you actually don't really know what you want the model to do. It's like, what do you want it to be good at? At everything, you know? This question is a little bit easier for people that have like very narrow tasks or very specific things where it's like, I know what I want it to do. I want an agentic model that, can like, help people on like phone calls, or that can like route various things between the API or write code, right? Like that's very well defined. I'm not saying it's easy, but it's like definitely much more tractable than like, you're a team, you're tasked with making the world's best open source model. What do you want it to be good at? Go, right? Like everything, right? The I think that the answer is like not a great one. It's like you essentially, what you're, having worked on one of these high pressure things where it's like, we're going to make an open source model, you want your boss to be happy, right? The answer somewhat ends up being like, go find the benchmark that everyone's most excited about and do a good job on it without cheating as best you can. Like benchmaxing is real. And you want to have the high score because that's what people are going to remember at the end of the day. But you also want the model to be good, so that way people don't feel like you did that. Yeah.
We are talking in a few days with the CEO, the co-founder of ML Arena. That
Oh yeah.
yeah, that is like the expert in benchmarking and how we can cheat on benchmarking.
So
Yeah.
I have a related question to this. I've always thought, first of all, it always seemed like post training, because they had so much less data, that they must be training longer, like more epochs, because it explains why slop is so slop, the way we define it, like certainly delve, it's not X, it's Y, so overrepresented. But then my question for you is, I always felt like training models, and indeed, we use terms like recipes because I think cooking is the right analogy, which is to say that it's extremely feels subjective, except that it has like scientific principles, and you have like multiple steps, but you can do them in different orders and get different, delicious models, I guess. What I'm trying to ask is, it always seemed to me like behavior like grokking, for one, and in general, like it always seemed like low and slow made more sense. Literally like low learning rate and
Mhm.
slow, basically saying, okay, it's going to feel compute inefficient, but maybe the quality of my representations are better. And I'm wondering then, in the context of trying to avoid benchmark maxing, or maybe benchmark max but also be good, do you believe in that kind of like low and slow approach?
I mean, I think that is kind of what is like, that's sort of what the big rise in RL represents, right? Is like, they have very little data. RL in some ways allows you to use that data like much more effectively without as many worries of overfitting. But like, it's very funny if like, I've been working on some like blogs to cover some like the weird history of data. Uh, uh, and going back and reading papers from 2 or 3 years ago to see what people were up to. If you read like the Llama 2 paper or the Llama 3 paper, it's so funny to see like what they were doing for post training. It feels so antiquated, even just a little bit later. But like even places that were well resourced didn't want to do online RL because it was just so hardware inefficient. Like the MFU was so bad that they absolutely could, and they just chose not to, which was kind of funny. Um, yeah, so I guess like that sort of is the low and slow if you think about it. Is like, okay, well, we're just gonna kind of take lots of shots at this and hope that we get really high quality samples, and we just don't care how long it takes us to get the high quality samples and the positives, you know. Yeah, I don't know how much it will prevent benchmark maxing in some sense. Um, I can tell you like how we went about trying to avoid benchmaxing as best as we can, and still like how we go about trying to avoid benchmaxing now at Datology is
Yeah,
like,
we'd love to hear it.
yeah, and I'm not saying that we have like the perfect solution, right? Like there is still this weird optimization where people want to be able to brag about being the best at important benchmark, but also don't want to have done that. And what we did at Mosaic was we had this thing called the gauntlet, and it was like 35, 36 evals, and we kind of split them up as best as we could into kind of like categories of things like language understanding, reading comprehension, programming, world knowledge, right? And then all of these kind of got aggregated into sub tasks, and then once again averaged into like one large task, right? So there wasn't an easy way to like maximize the score on one like eval if you like overfit that wouldn't hurt your whole aggregate. It was kind of funny because we were like, we really pitched this as like those charts from like soccer or like those Japanese RPGs with like the skill things. And like that was how we were thinking about it. It's like, okay, you've got so many points you can put into things, right? And you want to represent the whole. I remember coming out with the blog and putting the radar plot out, and like we angered so many people. They were like, "This is not the way you should ever plot data." And we're like, "Oh, sorry, we didn't
No,
mean
radar
to."
plots are great. I'm sorry, radar plots are an amazing way to do at a glance
Yeah,
understand like capabilities, and they've been used when you point out JRPGs. There's a time-honored tradition of using them in video games, and yes,
yeah.
I don't
I mean,
naysayers
it
are.
was it was great for us. We could at a glance very quickly see, what we had done. This angered a lot of people who had problems about it not being able like the interpretability and like the scientific rigor of it. I was like, okay, well, you're allowed to do whatever you want. You don't have to use this, right? Yeah, and that's that. But anyways, this way of thinking about things where it's like you need a holistic approach to what you want the models to do. You want to care a lot about the evals, and hopefully you're capturing capabilities that are aligned with what you want the model to do. Like in a weird way, if you know what you want the model to do and you know that your evals are capturing it, the data part is pretty easy. You just kind of pull knobs until you've done that thing, right? And that's also why benchmaxing is easy. You just pull the knobs until MMLU Pro goes up or live code bench goes up, right? And then you call it a
But
day.
I have another question. So, but in the pre-training, it's not clear, right? Because, right, post-training just maximize the benchmark. But in pre-training, it's not clear what do you actually want to do, right? What is the right metric to check? Even if you ignore fitting on a specific benchmark and you have several benchmarks that capture the thing that you want to do. What you're doing in pre-training, how you evaluate it?
Yeah, I mean this is a good question too, right? Like, I mean, this one was also very hard, especially a couple of years ago, because it wasn't really clear which things that you did in pre-training, the ways you were able to evaluate models that are base models, how they even transferred over to what would make a good model for post-training. Like, MMLU was like the thing to be good at for like years, right? And the funny thing with MMLU was if you got a high MMLU score, when you went to post-train it for, I mean, some of this has changed a little bit, but like you always expected your MMLU score to go down in post-training. It was just like the knowledge the model had, and you couldn't make that better. But it wasn't clear if that actually made the model better in the post-train model. You know, is like, well, it knows lots of facts, I think. Is that a better model? I don't know. You know, and it was really hard to figure out which evals correlated to the things you wanted to see in downstream performance. And I mean, I think generally this is still not entirely clear, but we did find that when we took this aggregate approach, this at least somewhat translated well, that like we were good at a broad, diverse set of things, and the models that had the higher scores there had higher scores than the post-trained evals. So that was at least, you know, correlated in that sort of work.
So today, like the best option that we have is just like to measure it on different like different benchmarks, even though like we didn't train on these benchmarks specifically.
Yeah, so I mean the thing that I understand that like really works the best, but is like much harder to do, is if you have holdout data sets that you're absolutely certain are not on the internet, and you transform them into these like Perplexity eval sets, right? So like I think a lot of frontier labs use their internal code sources, although I don't know if this works once you start vibe coding. You know, but like you have data that you're sure that no model has ever been trained on, right? And then you actually get a very predictive measure over the training course, especially the closer you can get the thing that you're calculating perplexity over to be the task you want. This works really well. I mean, it just, you know, it is the definition of what you want it to do. It's just much harder to go find those examples, you know.
Would you then agree, because I fully believe this idea that we are trying to maximize, like from an output sampling, like an output sampling researcher perspective, I want to maximize perplexity of my output while maintaining coherence, right? As a good proxy for the diversity of the output.
Um, Maximize perplexity while maintaining the coherence.
Yeah.
Um, I suppose, right, if you're trying to make something that is like less regular, more diverse, and I guess you could say more surprising, I think that makes sense. I mean, perplexity, like thinking in terms of pure perplexity is always a really funny thing because it's like it's so dependent on the context in which you're discussing it. Um, yeah, in that sense, right, it does make sense. Y- I think if you told a random researcher that you were trying to maximize perplexity, they would have a heart attack.
Well, no, but I mean, I am though in this case, which is, but grounded by my LLM as judge or some other, human source being like, that output is still good. But
Right,
it just
right,
seems
right.
like there are all these other measures of diversity of outputs, but perplexity, which is calculated via entropy, right? Which is, and so I've always felt like it's all there in the entropy too. And,
Right.
and yes, I'm aware that like gibberish has like maximal
But
perplexity, but that's bad scores on your coherence. So
yeah. I mean, like lots of creative writing and like poems and things, you know, follow these like little, you know, parts where there's like little lulls and then spikes, right? And like the things that kind of grab our attention tend to be these little spikes in perplexity where it's like, oh, I've said something very clever or different than you weren't expecting there, right? And I think so it's kind of weird how you want to, how you want to constrain this, right? You don't want everything to be high perplexity because that would be gibberish, but like maybe like the average sequence there to be high perplexity because you've kind of put in lots of interesting novel surprises and twists there. Yeah.
So, so it means that like for different data types, like you actually want different like metrics, right? You want even different perplexity, right? So do you think we actually need to split, to say, okay, so on this type of data we want this measure, and on this type of data we want this measure, and like somehow to combine all of them even in the pre-training?
Yeah, so now I think now you're asking like how would you gather some measure to kind of quantify quality of given sample points or given pools of data, right? Um
Or even like also like to train on these metrics,
Right.
right?
Yeah. I mean, I feel like there hasn't been a whole lot of success on kind of coming up with ways to like perfectly quantify data for pre-training. And the best examples really just kind of come from like you can use LM as a judge, right? And you can use quality filters, but like it's still very imperfect. And basically we're kind of stuck with empiricism, right? Um,
So just to make sure that like when you say LLM as a judge, you just take a pre-trained model and feed it with data and ask it to classify, like to give it some rate and to say
yeah,
like, do we need to use this data in our pre-training
yeah.
pipeline?
I think like for on the pre-training side, I think like the most famous and successful example is FineWeb EDU, right? And what they did was they made this rubric, and they said, these are 5 qualities that we want in a sample, and they're related to educational content. And for each axes that you see, like reward 1 point, and then you're gonna score a bunch of documents, so that you've got a score from 0 to 5. And then because like that was really expensive to do for the entire internet with Llama 370B, we're gonna then take those scores and train like a classifier on top of an embedding model. And like this worked unreasonably well. Like, and the funny thing about this too, to me, is it seems like they've tried. So one, it like kind of just works. They can just kind of copy paste this method and take it into new domains. You started seeing all sorts of EDU data sets coming out. Like you had the Stack EDU, and then you had Fine Math. What are all these data sets? They just copy pasted their rubric and changed some of the words, and did it again. But the other thing that's really funny to me about this is like it seems like they've attempted to make a couple of improvements on this, and they like haven't. It hasn't worked. Like they just nailed it the first time. Like they were doing this kind of like grade school to like early college math, and then they've tried to make other rubrics for like graduate level math, and like the models don't care. They don't want to learn graduate level math. This hasn't made them any better at anything, which I think is really funny, and part of why it's really hard to understand what's going on. But like that's like kind of the height we have right now of on the pre-training side is like, and then you look at a bunch of these documents, and like it's not actually clear when you're looking at it that these are good. Like they're very strange documents that you pull out from these filters, even though you've used a model to judge these and say that they're good, right? But
Strange in
but the
what way? Like what? Why? What do we see there?
So the documents that tend to be judged as like high quality from FineWeb EDU's classifier, they're very short and they're very information dense. Um, and I think it's interesting because I think we're still learning a lot about how models learn, right? It wouldn't have been obvious ahead of time that that is actually what you want, right? I had a project with an intern of mine who was like working on developing some filters, and we wrote these complicated ones with like, okay, we want to have like health blogs and science and technology blogs, and we'll give some scores for writing quality. And we pulled out these documents, and they looked great. I mean, they looked like they're really well written blogs and all these things. And we trained some models on it, and they were just terrible. Like it was like the FineWeb EDU classifier just like swept the floor with it. And it was like, okay, well, this is good text. Why is this not make a good model, right? And I think it had to do with like there's this information density thing that like wasn't really obvious that you needed for training a model. That it wasn't good to train it on a bunch of examples of these like really long prose. Like if you think about how some of these like cooking blogs start, where it's like, well, when I was 12 years old, my mother used to always sit me down at the table and do the smell of this thing, right? It's like actually what the model wants is, can you take me to the bottom with the recipe? Like, uh, yeah.
So do you think like if you will let I don't know, like you will extract some features from these documents, high quality document, do you think what that they contains a lot of information regarding a specific task, or like this is something about the natural language, or what are the features that you actually need in order to train good models?
Yeah, so I mean, the successful and like popular filters, right? They're in some ways just aligning the pre-training distribution for the task distribution, right? So the other really popular open source filter is the DCLM filter, which came from like the data comp paper. There was like a competition for who can train like the best model from open source data, right? And that filter took a different approach. Instead of kind of using LLM as a judge, they actually took samples of data sets that they knew to be high quality, and then they essentially built a simple like n-gram classifier. But the data sets they chose was Open Hermes, which is an SFT post-training data, like question answer data, and then explain like on 5 Reddit posts. And so what they did was what they end up doing is finding in the wild a bunch of things that looks like instruction data, or looks like question answering data, or has like people explaining things. And you still end up getting a lot of these like really short information dense documents out. And it makes a lot of sense, right? If you want your model to be a chatbot that explains things to you, you probably want to find a lot of examples of people explaining topics to people, or answering questions, or helping them.
So, these filters, have you seen like innovation in them in the past few years? Like, are there new filters in 25 and 26?
I mean that's the thing that's kind of odd. There's not, right? Like there was these FineWeb EDU and DCLM, I think, came out within like a couple of months of each other. And then there hasn't been anything that's like really killer that blows it out of the water in the open source since then. Like now I know that like every big lab that's doing things probably has dozens of these that are probably very useful, but it is kind of odd that it's like these just kind of came out, they were incredibly effective, and that's it. That's what we got. They're not that hard to replicate, maybe, and I'm sure someone is sitting on something that's like really awesome. Yeah, that's what we got.
Okay, so l- now let's assume that we know what does it mean to have good data for pre-training, what we want from mid-train or post-train. Let's start with high-level uh, um, principles. What are the good properties for data in these steps?
Yeah, so this ends up being a lot of your like math data sets, your code data sets, some of your really high quality things, maybe like academic papers, Wikipedia, um, it may things maybe that if you've made very specialized filters to find specific types of things, maybe you put some of those in there. And like categorically what you're looking at are things that you have maybe like billions of tokens, whereas like your large scale web data may be trillions of tokens, right? And you're trying to figure out, okay, I've got maybe 5 billion tokens of Wikipedia, and I have a 20 trillion token training run. How do I use this well, right? Or on the entirety of GitHub that I'm allowed to scrape, there exists 400 billion tokens of code. How do I reasonably make my model train on 20% code for 20 trillion tokens, right? And that's kind of the question of like, what are you attempting to do in mid training, right? It's your most valuable data, the thing that aligns most with the distribution that you care about, maybe your highest quality data, either by these filters or however you've decided. Uh, uh, and then like, okay, now how do I use it? Right. Yeah, and it's kind of a funny story. Like maybe me and the people I worked with at Databricks kind of ended up doing mid training by accident. Like we weren't intending to do mid training to make models good when we started. We just had this problem of scale that we had to address, which is like, okay, we were not GPU poor under any ways you define the word, but we still couldn't be like reckless with our compute, right? If you have 512 H100s or 1,000 H100s, you still can't do like a hero run level sweep on every possibility of your data, right? We had very limited, like we could train essentially like a Llama 2 7B in about a week, but we couldn't train 10 of them. and we couldn't, test every permutation. And so, what we originally were doing, when we were starting to do some of the things that are now called mid training, was we were like, we have all these small data sets, and we think some of them are really helpful, but we don't know which ones. And what we were hoping we could do and turned out to work was, well, what if we take the data distribution and like the last 10 or 20% of training and we just move everything around, right? If we just upsample the data sets we hypothesize are helpful for this task, maybe it will tell us. It turns out it does. And so then we were able to kind of like grok the relative quality of our small data sets to like a much more accurate degree, where we couldn't have done like 100 sweeps. We can now say, okay, actually this open web math data is really helpful, or this data set here is really helpful, in a way that we couldn't have, just because there's only 5 billion tokens of it. You couldn't possibly have trained on that much of it.
But do you think it's only a matter of compute, like mid-training? Because let's assume that I have infinitely amount of compute. Do you think it's worth to just train on all the data and like just remove the mid-training?
So, I mean, the problem is not the compute. I mean, the problem is being data constrained, right? It doesn't matter how many GPUs you would have given me. I still only have 5 billion tokens of Wikipedia, or I still only have 5 billion tokens of this math data set, or this, or 100 billion tokens of Python data that exist, or something like this, right? And so when you look at like how you train models and like scaling walls, right? No amount of training just on code data, if you only have 100 billion tokens of Python, you can do 100 epochs of it. It's never going to give you the signal you need. She has lots of thoughts about mid training as well. It's never going to give you the signal you need to know what is the good data or the important data for the Python, right? So like in certain sense, this is just kind of like a necessity. Yeah. If you gave me 10,000 H100s or B200s or B300s, I still have a limited amount of data.
But I'm not sure that I understand, because like then like I think these models can fit everything, right? So if I have like so why to use only small subset of the whole data, right? Like assume that the model can learn like both math and English really good if you give it enough compute and make enough iterations. So why not?
Sure. Yeah, I mean, so like I guess you're kind of saying like, why worry about uh, the proportions or what the data
Yeah.
is, right? You just go big enough. And you're right. If you train like a trillion parameter MOE, it'll sort of learn everything, right? You just give it enough tokens. But in a sense, though, the models are still learning these probability distributions, right? If you give it, if you just went and got 10 trillion tokens of web data, right? It just learns to like approximate the web data, right? And the problem you have is, even if it has learned all of the concepts of programming, the probability of it generating that will still be very low. So like you are trying to capture some distribution of text that you want the model to be able to recall and produce easily. And shifting that probability in post-training is like pretty hard. If you're able to do it to some degree, but in certain sense, right, what you have when you get to post-training, you basically have what the model's priors are. And you're able to sharpen it a little bit, but it's very hard to push it. If you don't train it on any code, it's very hard to make it, even if it's read enough concepts to grok it over the course of reading the internet, to make it actually be a software engineer. So that's a little bit why we care about these small data sets, is because they represent the distribution that we want to model. And it's very important for us to be able to kind of push the model into that direction before we get to post-training.
What do you think is the future of the quality or of post-training or pre-training data sets, even now that so many of the sources of getting that data seem to be drying up in various ways? I mean, Stack Overflow is dead. The internet at large is overran by LLM and related AI generations. And companies are becoming very data protectionist now. So anybody with any kind of unique data has hoarding it and making it very expensive to get licenses. So what do we do in the 2030s?
Yeah, I mean, well, I guess I had done this like fun little like thought experiment going back to the FineWeb blog and looking at the tokens that are being produced. So one thing that's kind of interesting is you're right that people are becoming more protectionist. Like Reddit shut down; you can't scrape it anymore legally, um, and Twitter shut off its APIs, and websites are doing this. There was like a big dip in common crawl tokens that occurs. Maybe it was like 2022, 2023, something like this. The funny part is that it's like completely recovered. So like every month common crawl is producing about as many tokens per month as it was before. Now, I mean, like, this is not going to get us completely out of like data jail if you need to continue to scale to these massive sizes. Like, you get 150 billion new unique tokens every couple of months. That's like, if we want to train a 100 trillion token model, we'll be ready to go by in 70 years. you know but we may want to do something a little faster. I think this is where like synthetic data has really come into like a place that's like really valuable now. And maybe to answer like one of the questions you had is like, okay, why are we doing this mid-training thing? Like, my thoughts about why we do mid-training has evolved a lot, having seen like the more advances in synthetic data for pre-training. In some sense, like, you can actually stop doing mid-training if you have really good synthetic data. It's like, if you think about the question that I was posing about like what were we trying to do, is like, well, we think we might have some small data set that's really valuable. And maybe we figure out the answer is yes, this data is valuable. We've measured it empirically, or we've got some score. And if you have really good synthetic data, then the question becomes like, what if this data wasn't rare anymore? What if I can take this 5 billion tokens or 100 billion tokens and make it 1 trillion tokens? Then what would I do? Would I need to do this silly little thing where I kind of push the percentages up in several phases, or could I just train on that? I think that's an interesting thing that's going to change in the future, is we're getting much better at that.
So do you think like in the future, or like maybe now, if now I need to quantify how much like each token worth to my model? So one option is that, yeah, you have just random token from some random data set, or like pre-trained data set. Another one is that you have random token from I don't know, from post training or mid training data set. And the third one, maybe it's the one that you choose based on, I don't know, some FineWeb method or whatever. And the last one is synthetic data. Which one now I need to choose to get efficient I don't know, scaling loss?
Yeah. Oh, scaling laws, or you mean like a model that will scale to like good performance?
Yeah, a model that will scale for good
Yeah, I mean,
performance.
the answer right now, I think, is kind of all of these, which I know is not like a very satisfying answer. At Datology, we do a bunch of synthetic data. I think like when more models were starting to use synthetic data, maybe a year or two ago, like the Microsoft models and some of the Google models, there was this like very strong knee-jerk reaction about like model collapse and dangers of using synthetic data. And I think that mostly came from the fact that they were kind of prompting models in a way that was like pure, almost like distillation. They were like, give me a textbook about math, give me a textbook about this. And you really kind of, when you do something like that, you really limit what you're able to get by the quality of the teacher, right? There's like, how much diversity can the larger model generate, and how accurate is it? And like, if you look at the kind of like we were talking a little bit about like surprise perplexity over sequences earlier, right? LLMs don't generate that naturally, right? So you're going to get a bunch of just like really regularized stuff. Maybe some might even call it slop. uh you know and I think that what has changed recently is everyone's kind of moved to this like rephrasing paradigm, which is you're actually pulling a bunch of unique seeds with a lot of diversity from the internet or from coding examples, And then you're looking at the model to figure out how to augment this, either to align it better to the task you want to do, or rephrase it in a way to just increase the diversity, or like the allow you to use it more. And in a way, this kind of harkens back to the image days, where it's like, this is the data augmentation we were looking for. It's like, this is the random like flips and crops and noise, in some sense, is like, we can do this with data, with synthetic data. And now we can ask the question of like, okay, why mid-train? take all the good rare data and make it not rare.
So so now I want to create synthetic data. Let's assume that I believe that this is better. Like, what is the best way? What is the best pipeline to make it? Like, does it matter if it's pre-train or post-training? Do you think we just can take post-training types of question and just train on them? How are we going to do it?
Yeah, so I think that like the synthetic data in pre-training actually has a lot of catching up to do with the work that has been done in post-training. Like, post-training, I kind of, in a lot of ways, is almost all synthetic data at this point. I like very I'm sure that people are still getting human annotations, but probably far less than they were like 2 years ago. Where like this was actually the bottleneck for post-training a model, was you had to go pay Scale or some company millions of dollars to give you tens of thousands of handwritten examples, right? It's like, well, now I can just go get a Quinn model or Kimi K2 or something to do something 10 times better and generate, I can get a billion tokens for post-training. That's just like completely changed the tractability of doing post-training as a small shop. In pre-training, though, like it's very funny. Like, if you look at the papers that come out for synthetic data for pre-training, they're like very simple, and they're not nearly as like nuanced or as advanced as what was happening in post-training synthetic data even like a year or two ago. And I kind of have this joke at work where I'm like, everything is either like Persona Hub or it's Eval Instruct, and they're just like in a trench coat. Like, if you look at that's basically, those two papers are basically all of the way that people are doing pre-training data in some sense. You can follow it like 3 steps down, but you'll find like, okay, there's this math synthetic thing, and you follow it down and you're like, okay, actually it's just Eval Instruct again. um
So
yeah,
they basically prompt the model to some like specific definition, right?
right.
To
Like, so
some
the like
specific types of.
yeah, I think that like the prompting strategies have not gotten very advanced for pre-training. Maybe this is just because of the scale that you need to do. I think that there's a lot more interesting things that can be done around like building like, knowledge graphs and figuring out how to combine lots of diverse data into complex contexts to make interesting samples. Yeah, maybe all that is to say is like, synthetic data and pre-training is really in its infancy, and it's already unreasonably effective, and I think it's going to get much better.
Doesn't it seem like you're trading compute for better quality, right? Because, even Elon has gone on Twitter and said, well, we can just, use LLMs to data augment what we have in a million ways to basically extend to an unlimited amount of tokens. That seems a bit intuitive, maybe not to the extent that he proposes it, but it seems intuitive to me.
Yeah. I mean, why not, right? Like, the good thing about spending your compute on data is it's a one-time expense, and if you're successful, right, or a one-time failure, and then you can use it over and over again. And so like that has a lot of benefit. I think that what's interesting though is we still have to kind of learn some of the fundamentals about how models are learning these tokens to do better with synthetic data for pre-training. Like, a really simple example is like, if you were to try to train a model to do like arithmetic and multiplication, and you had kind of sort of like a toy example of this, where maybe you have like millions of examples, or basically you generate synthetic data sets that, does every single example of addition of 4-digit numbers that can be possible, right? And then you hold some of them out to verify that the model can do this. Like an LLM probably isn't going to learn arithmetic that way, which is kind of interesting. Like you've shown it every possible way to do arithmetic. Why can't it do arithmetic, right? But if you train it on large enough web scale data, it will learn to do arithmetic. And so like there's something that's interesting about how you transform these data, like what the model needs in its context to actually start developing these like circuits to learn that are not just obvious from like this example does this thing. Like that's not sufficient.
So do you think we can go all the way to pure synthetic data sets?
So supposedly this is what the GPT OSS models were. And my understanding for why they went all synthetic for the GPT OSS models wasn't because they thought it would be the best performance. It was like entirely liability. like like they didn't want to be sued for whatever kind of data sets that they train on internally. Maybe they've gotten the licenses. I'm not making any claim about this, but my understanding from my friends that I've talked to is like there was almost entirely synthetic rewrites of everything that went into it as like a kind of like a licensing whitewashing. So if you like the GPT OSS models, that's supposedly 100% synthetic. So not everyone likes them. So
Yeah, it's also not clear what does it mean, right? Like if you just take like a model and the model like just generate the same data as like the input, right? Or like does it mean it's a synthetic data set, right? Um,
yeah,
and
it's a good.
also and also like we have like I think I saw on Twitter someone just um jailbreak models and they generate books, right? Or the Harry Potters and things like that books from the models, and there were models that they can just generate. I think it was like 95% of the books of Harry Potter. Um,
No, I've heard it was 98% now. Well, and
maybe
actually I wanted
98.
to also related to that, it seems like um copyright infringement and data sets that even probably at the time were clearly so-called like nobody has the rights. I don't know. I work at ThoughtWorks, and so Aaron Schwartz, he's
Oh,
a ThoughtWorkser right before he died. So this is very near and dear to our hearts, and you can imagine that I'm actually allowed to kind of be a little bit advocate a certain level of copyright abolitionism, even with a little bit of my. But I guess what I'm curious is how do you see all these issues? Like how because it seems like the original sin of generative AI, as I always called it.
yeah. I mean, it's tricky, right? Um, I have been surprised from some of the court cases that have come out against like Meta and Anthropic, um, how I mean, frankly, how supportive of their rights this has been. Like in the fair use direction. I don't think that this was as clear like a year or two ago that we were going to see so much support for model training have these fair right protections. I mean, so like Anthropic and Meta have been getting in trouble. But like if you look at the decisions, they're getting into trouble for things that are not actually having trained on the data. It's like how they acquired it, or what they did, what their usage was, which like really surprised me. Like I didn't think that there was any version of you've got a bunch of pirated books and you trained on it that was going to fly, and apparently there's some nuanced
Well,
discussion of that. Um,
I mean, there has to be a little bit, right? Because if we're going to put everybody as responsible for what they train on, if you train on a large enough slice of the internet, as the Stable Diffusion people figured out, oops, we get illegal content. And I don't think that we should be putting any AI researcher who's acting in good faith in jail over a 1 billion image scrape that just happens to get some CSAM, right?
yeah,
Yeah, but
yeah,
do we want? But it's different to, I don't know, to claim that like one research is guilty or not versus like a corporate company that put billions of dollars on it and earn billions of dollars from it, right? So like I don't know what I think about it, but I think like other like it depends on your basically on your what you want to do with these models and like how much money you're going to earn from these models.
Yeah, it's very interesting to you know, I this is this is probably the most third rail topic we're gonna talk about all day, I'm sure. So my wife actually is like a graphic designer and artist. And it may not surprise you guys or any of your listeners to know that like in the art community, AI is like a whole other thing. Like it's very controversial, with like, fair use and copy and things like this. And so her friends had a lot of things to say about this, and I'm sure it's been very exciting for her to have to deal with me having the career that I have, and maintain relationships with her friends. And I remember it felt like a year or two ago, the discussion was like, well, the problem is that the models are trained on stolen data, right? That's like the kind of the thought process from the artist was like, the data is stolen and this is what's the problem. And they're benefiting off of this improperly licensed data. And this is a problem. And like, good point, I guess. And I was really excited when one of my interns at Mosaic was working on this open diffusion model where everything was correctly licensed, right? So there was like no problem about the generation. I can't remember what the name of the paper is. I feel bad because I can't plug it for him. But it was like an all open data stuff. So everything was fair. Like,
Put it after it.
yeah.
Don't worry.
Um, and so anyways, they released the diffusion model that's like completely perfect, like proper licensed. And I was like, Bridget, you have to tell your friends, they'll be so excited. We did it. We stopped the art theft. They were not amused. Like, it was very clear that like whatever the argument was, it was like that was a convenient argument, and they were really upset about the potential for like lost revenue and jobs, which like, okay, I don't know why I don't know why I had this like optimistic view that it was like we're gonna change everyone's mind as soon as we just listen to their demands. And it was actually like, I've got all these fears about the future and technology, and this has done nothing to dissuade me that AI can be good.
Yeah, no, I'll just put on that. I will say the reason you might have assumed that is people in the art and similar kind of creative communities have often professed political egalitarianism throughout history, up to and including, being at one point card-carrying supporters of groups like the Electronic Frontier Foundation and others. And wow, how the turns have tabled as things shifted. And I realized a lot of people became copyright trolls defending the RIAA, MPAA, and suing grandma circa the year 2000 for trillions of dollars. Like, I did not realize how quickly that would shift in the public, even from the very same people who express so-called egalitarian beliefs.
Yeah. So that's probably as much as I'm going to say about copyright.
So I want to go back to the efficiency of synthetic data. And so I have a question. Do you think right now we are generate synthetic data in the token space, right? Like we generate the actual text, but in principle, like we don't need to do it. Like there are all these models, right? Like Coconut, for example, that make I don't know chain of thought in the representation space, and I don't know the loop transformer and things like that. Do you think we can move from synthetic data with tokens to a representation space and to actually make synthetic data in more suitable or more efficient way that the models actually can use it without tokens?
Yeah, I mean, it's a good question. I think that the lines really get blurred too when you talk about, can you do this data in the latent space, and or versus like, how is that distinct from doing like knowledge distillation? When I was in grad school, actually, I really wanted to make a bunch of like synthetic data in the like the latent space form, and so I had all this whole thing where I was trying to like generate like feature maps of like convnets, and try to like make distilled versions of like every feature level, diverse sets of things, right? To like maximize like neuron activity and things like that. I mean, I think it just ends up being very hard to know what you're doing, right? If you don't have a way to ground yourself in what you're getting the model to do and you're generating stuff, it's very hard to like measure that you've been successful. I'm not saying no, that I don't think it will work. It's just hard to imagine a way to move quickly in that field.
But in some way, like all the synthetic data is distillation, right? It is still the model. So do you
Yeah,
think there is
yeah.
something fundamental, or there is something like more, I don't know, like easier to base it on text?
Yeah, I mean, so like I think that there is a distinction though when you go from these like kind of textbook pure generation things where you've kind of like all of the text is generated from a teacher model to things where you're doing rephrasing or augmentation, right? Where like it's like very constrained generation in some sense, and it's not all from the model, and you're kind of injecting novelty and new information by doing this rephrasing. So you get something that's very different than you would from distillation.
And do you think so? In another related topic, do you think we can get, very efficient data curation, synthetic data? For example, Phi, right? This is like the canonical example, the Phi series models. Do you think we can push it farther, and we can get like, I don't know, 10 examples that will teach us everything on math?
Yeah, I mean this is a hard thing to know, right? Like I think that you're going to be more successful no matter what, the more starting examples you have, right? Um, it's certainly we're certainly going to get to a place where having 10 examples, you can do much better than having no examples. And it's better than nothing. But I don't know that you're going to get like the same. I would be very surprised if you're going to get the same quality out of like tens or thousands of examples than you would if you have millions or billions of examples, right? So I think there is some sort of a constraint there.
And do you think this is different between pre-training and post-training? Do you think like if we have enough data in the pre-training, like we can make kind of like few shot learning with synthetic data better?
I do I think it's different? I mean, it must be different in some sense, right? Because like synthetic data was so much more successful so early in post training in RL, that like there's clearly something where it's much easier to define this task and do this. Um, like, are we going to make better models? Absolutely. I'm not sure I understood what the question there was for what you want to do with the pre-training.
So the question is like, okay, so do you think now, okay, let's assume that like we are creating very efficient examples, okay? So one option is to have these very efficient examples and to I don't know, to distill like billions or trillions of examples from the pre-training to, I don't know, 1 million examples, and now you can train it with 1 million examples. And this is one for the pre-training. But for the post-training, let's assume that now I have billions or trillions of examples in the pre-training. Can we use 1,000 examples in the post-training, like 1,000 synthetic examples in the post-training, in order to align our model? Do you think this is different, the two
Yeah.
cases?
So here, I mean, maybe like one thought I have about like how we're doing synthetic data and mid training, how we're aligning post training and pre training, I think is like, so like, um, I think there's a really exciting direction that I think people are all like beginning to head toward, and I think is where kind of pre-training is kind of going to take some like mind share back in the world, which is like, okay, so RL and RL environments are like the hot thing right now. There's dozens of these RL environment startups, and it's like not for no reason, right? It's very good at like if you can define your task, and you can put a model in this environment and you can kind of get it to do things, you can kind of train it to do these things, right? And my understanding of where this is difficult is like once you kind of leave the like normal safe space of the model and you try to get it to do genuinely novel things, it's very hard to get successful rollouts, right? Like you may have rollouts that are like, your success rate when you start the task is like 1% or 2%, right? And so then it's going to be like almost impossible to reasonably train it in this environment because you're going to have to start from like basically nothing. And it just doesn't know what to do, you know? And I think what's really exciting is like, well, now people have been demonstrating with mid training, which, when I was doing it originally was like, I just can't get signal. I don't know if Wikipedia is good, right? Now people are doing really cool things with it, which is like, we can actually shift that starting rollout percentage. If we can find the right data, we can make your RL success rate at the start of training go from 1% to 10% or 20%. Right. And that is a huge game changer. Now you can do this. Right. So I think what's really interesting is like the interesting question isn't really like, what do you do with synthetic data in post training versus pre training? It's actually kind of like, how do we like close this loop? Which is like, let's take where we're failing in post training. Let's find the useful examples, like the successful or unsuccessful rollouts or a model that can do the task versus the one we're trying to get. And then let's figure out how to contextualize this problem and bring it to a pre training scale and use mid training to align the model and see if we can do this, right? And I think that's something I'm really excited about is like, can we make pre-training cool again? Can we like use mid training to make RL more efficient and more successful? And then can we just like close the loop? And then, instead of having to ask ourselves pre-training, mid training, post training, what's the difference? Like we just have training.
Well, and then what about incremental and continuous training, right? Like just keep doing it on new prompts on the fly, right?
Yeah. I mean, man, I don't even know what if you had to define what is continual learning, like truly. I'm not sure that I understand what everyone means. But certainly there's definitely incremental things you could do, right? Like as you kind of discover these tasks where you have bad coverage, right? You can kind of generate new data and like re-kick off these pipelines. The real continual learning, the holy grail continual learning, that frightens me in some sense.
It's like I just saw a post someone posted that there is a lot of discussion about continual learning and a lot of solutions, but for me at this stage it looked at like you just can put everything in a memory.md file, but I'm
Right,
afraid to
right.
ask what is the problem.
Yeah, yeah. Yeah, yeah. I mean, it's a good question, right?
But okay, but do you think we can actually like really combine RL in this pipeline to help us to like to filter the data and like to come up with better data points?
Yeah, absolutely. I mean, like I said, I think that there's a lot of interesting work. Like there's a paper, the Octothinker paper, where they did this, where they specifically took like one of the weak Llama 3B models, that like, you basically couldn't get it to have any success rate in RL for like these math topics. And they do a bunch of mid training on it, and then boom, like now it's just as good as Quinn at RL when you want to train it and to teach it these things. And then like it's a pretty simple example, and you got to be gentle with the grad students, right? That was like it still matters. But I think it's like a valid proof of concept, which is like if you've defined a verifiable task or an environment, and you can't really get a model to do it, there probably is a way to close this loop with mid training, and to figure out what is the gap in its capabilities, what is the like the prior that it needs, or like the distribution of tasks that it needs to understand to as a prerequisite before this RL step is valuable. And I think that like being able to get better at this iterative process of like we go from we can't do task to we can generate data that helps do task. I think that's like a really exciting direction for data in the future.
And do you think in the future we will see models that are more specified in one domain and one problem, or like we'll see fundamental models that are good on everything? And of
I
course,
mean,
it's
we're
related to the
almost gonna
data.
Yeah.
how they
We're
train
always
it,
gonna get
right?
the frontier models that are good at everything, right? I think that we're going to see a lot more domain-specific models. I feel like people have been calling this for, like, 4 years, and so I don't wanna be, like, the latest person to, like, keep predicting this. But I think that what is, like, fundamentally changed is all the tools you use to build this are just so much cheaper and better now. Like I mentioned, like, if you wanted to release a post-trained model in 2022, you needed an army of annotators to give you preference data, and you had to train preference models trained on this, and you had to have done a good job of like inner annotator distance. And then you can either do your preference RL or you can do like offline RL. And now you can just like get Kimmy K2 to just judge everything you do, you know? And so like there's lots of very smart people that have, you know, lots of Fortune 500 companies and people that are doing enterprise work have little pockets of very talented people, and they like know what their domain is very well, right? What was missing was like, well, they're not going to get a $10 million annotation contract from Scale, and they're not going to get an army of engineers to do all this other stuff. But like, I think it's very tractable now to say, okay, actually, I want to make a very specialized model to handle, you know, some sort of like labels for, you know, like uh I don't know, I like if you've got insurance, you know, claims, right? Like you can do that, right? And I think that I think that is going to be a lot more popular.
Well, I'm curious on the domain specific model side. I mean, it always seemed like we're going towards bigger models and bigger data sets and more generality, right? I mean, including like Claude Code being for very much more than code, right?
Yeah, I like the thing is like there's just only so much you can stuff in a model without making it bigger. And at a certain point, these like scale differences are going to make the economics not make sense, right? Like, you can train, you know, like a sparse, you know, like 26B active 1 trillion parameter model to do everything, and then you can RL it to do your legal like document classification or your finance work, right? But you could also get, you know, like a 10B model, dense model to do that if you were able to find the good data and train it to do this task, right? Maybe with distillation or whatever. It's like there's gonna be a point where the inference cost of trying to do this at scale is just going to demand you to find a smaller. And it's not really about the capabilities, right? You're always going to start with the best model that can do your thing and hope that in the world of models that exist, there's a model that can do your thing. But eventually, once you've proven out this business need to get it to scale into something that you're going to do at really large scales, you probably just want a model that's specialized for that.
Makes a lot of sense.
Okay. Okay. Maybe we'll go to the question from the audience. So there was one question that talks about the pipeline of like efficient sampling or how to make like efficient data, and they say, right, that like the pipeline is mostly about the representation, right? Like you're taking your original data, you're extracting some representation from a pre-trained models, and then you select it, right? We talked about it it can be based on the LLM as a judge, it can be diversity, confidence, whatever. Um, and the one of the common concern is the pre-trained model and what are the biases that it actually inject to the selection. And do you think that we will see ways to improve this pipeline that we can get away from the biases of these models?
Yeah, I mean, so it is a good question. In some sense, right? Like, I guess you're never going to be completely free of it, right? Like, if you do something like in-gram models, like and like do some like hybrid embedding search, right? You move from one bias to another bias, right? You know, you can I think, you know, a good option maybe is just having like diversity, whether it's like diversity from your judging models and prompting, or how you're doing the feature selection. But you're still kind of stuck, right? You know, there's going to be some bias that is injected, right? And you just kind of have to ask yourself, can you live with it, and are you accounting for it, right? Yeah.
Okay. Another question is about the optimal mixture, data set, data schedule that interact with scale. Okay, what is the optimal one, both in terms of tokens and model scale?
Yeah. I mean, so this is a great question, and is like one of the most infuriating questions. So like the problem is that the right data mixtures do change with scale. And for a couple of reasons. One is it especially is going to change with scale when you're data constrained, right? If you're trying to design a data mixture for 10 trillion tokens versus 20 trillion tokens, regardless of like what are the capabilities you want, if you try to obey this rule, this heuristic rule of how many epochs you can use the data for, you're going to have to make a different data set, right? Or you're going to have to make some severe compromises or some interesting choices, right? And maybe this means like much more aggressive mid training where you're going to use far less code in the beginning and then you're just going to dramatically increase it at the end. Those kind of compromises are relatively straightforward. Not any more fun to deal with, but just like obvious, I guess. And then there's like there definitely is interactions with scale. Like let's say we're not data constrained at all, right? Um, when you're training relatively smaller models, relatively being key, right? Like even like an 8B model trained for 1 trillion tokens, which is like would make every grad student like salivate to train, right? That's a small model. The optimal mixture for that looks very different than the optimal mixture to train, a big several hundred billion parameter MOE. You just don't need to be as aggressive in the distributions, right? Like if in a smaller model, you're really trying to kind of overemphasize all the small tasks that you want to do. Like you're going to go way heavier on the amount of code that you want to do. You're going to go way heavier on the specific tasks you want to do. And then as the model gets larger, you do want to increase the diversity and things because like, well, on one end, you don't like you don't get anything more out of overemphasizing these narrow tasks. And on the other end, you probably are not really able to capture what it is you want it to do anymore. Like if you train an 8B model, you want it to write some basic Python programs, and you'll be very excited if it can do that and if it can repair code, right? But if you train a really large model, even your ability to like define what you're trying to get it to do is like very difficult, right? So you kind of have to kind of hedge your bets against what you think the data is doing, and just accept that you're going to put some weird stuff in it and hope that there's something in the distribution that captures what you want. That's a little bit about the scale. I guess I can talk about like the optimal data mixtures and data schedule that interact with it. I think it's a very similar thing, which is like you need to be much more aggressive about the mixture and scheduling in smaller models, or it seems like you need to be more aggressive. Then when you do a larger model, you can be more subtle with these distribution shifts, and it seems like you get better results in that sense. Yeah.
When you say scheduling, you mean about the training dynamics, right? Like where to put like different types of
That's right. Yeah. So
data.
like, I guess we've been dancing around the word mid training this whole interview, and we haven't actually like described what I mean mechanistically is happening, right? So like this generally means, although it can mean lots of things, what I mean is like there is a point in which the training, you change the distribution, you change the percentages, right? So if you imagine like at a high level, you have some hierarchical buckets. You've got like your code data, you've got some like math and STEM data, and then you've just got your web slop down here, right? And like maybe at the beginning, this is much more web slop, much less code and math, and then there's going to be like a discrete point where you go, okay, now the code data goes from 15% to 20%, right? It's like a really discrete point, right? Um, and like that was kind of what people were doing like a year or two ago, and now it's kind of broken up into like even more phases, like more discrete points. So you have like 2, 3, 4 phases of data changing where you're kind of doing these distribution shifts. And I guess what I'm saying is like for smaller models, you actually want these shifts to be even more dramatic and extreme. You kind of need them to be to kind of elicit the skills you want. And for larger models, it seems like you don't want to do that quite as much.
Okay. So do you think, like, one last question, do you think, we talked about it a bit, but do you think at some point synthetic data will be fundamentally superior to the human distribution it's based on?
Yeah, I saw that question come up on Twitter. I think it's a good one. I mean, I think it depends a little bit on how you define it, which is kind of a cop-out answer. Um, I think that there will be a point where training on synthetic data is better than training on human data. Um, do I think that models are fundamentally better than humans at like producing individual samples? I don't know if that's true. And why I like, maybe that's true. Maybe it's actually we've reached the point where we have God in box. The machine God has been built, and like it will become a better writer than every human. But I don't think that that's true yet. But what I do think is very likely is most of the data, even the good, high quality data we want, isn't really designed to teach models things that we want it to do. And so there will be a lot of value in transforming the data to do what we want the model to do. And I think that this will exceed like natural data performance at some point, where you would be silly to just be training on non-synthetic data, and you should definitely rephrase your things or do something.
Okay. I think we don't have more time. Do you have anything that you want to add? To
Uh,
advertise?
no, I probably should have thought of something, but it was really great. I'm really thankful you all had me on. Yeah, it was a fun conversation.
Yeah. Thank you so much that you came.
Yeah, all right.
And
See you
thank
guys.
you, Ellen.
It was a pleasure to be here and a pleasure to get to meet you, Cody, and to pick your brain.
Yeah, hopefully
Thank you so
sometime we'll
much.
person sometime. Like, I'll let you
Yeah.
know next time I'm in New York.
Great. Bye, everyone.
Bye.